Hello, everybody. I'm glad to participate in this conference. Well, my topic is related to technical development in vehicle, which is robust model predictive control applied on a PMSM electric drive system. These are the contents of my presentation today. First of all, we start by an introduction. Secondly, I will present the drive model. After that, we explain the traditional finite control set model predictive control, and we will see below the presented robust strategy, and to validate our study, a simulation and discussion of the result will be presented. Finally, we will finish by a conclusion. So what is an electric car? Electric car, it is an electric vehicle which are powered by an electric engine and electric energy. And for that, a lot of research had been and is still being done in order to introduce this environmental friendly vehicle. The vital organ in it is the control system, which is considered as the vehicle. The brain determines the entire vehicle performance, as it is the key to improve the motor efficiency. This figure shows the schematic diagram of the most important components of the electric traction system, which is an electric motor powered by a battery via an inverter, which transforms the DC voltage to alternative voltage, and all this is controlled by a strategy taking into account the dynamic of the vehicle. In this work, a common used three-phase source inverter is coupled to the permanent magnet synchronous motor as shown in this figure. This inverter has 8 different switching vectors accordingly, when 8 voltage vectors are produced. There are 6 non-zero vectors and 2 zero vectors. And here, the mathematical model of the PMSM or the permanent magnet synchronous motor. Here is the direct and the quadratic current of the stator, and the electromagnetic torque and the speed in the DQ rotating reference frame. And for the traditional finite control set model predictive control here, there is we use Euler method applied to the time continuous model with a sampling time period, and give us this the discrete time of the permanent magnet synchronous model in the rotating DQ frame reference, and expressed by this equation. And here the schematic of the traditional schematic diagram of the traditional finite control set MPC. Here there is a 7 vector are predicted by the discrete time predictive model. Then the 7 predicted vector are evaluated during the whole sampling period in order to choose the state that minimize the cost function and achieve the minimum absolute error between the predictive current and the reference one. The cost function formula is defined by this equation. There is 3 parts. The first part indicates the reduction of the reactive power, and the second part is the tracking of the torque producing current, and the last part is the maximum allowable stator current of the permanent magnet synchronous motor. And due to the drawbacks of the traditional FCS MPC or finite control set model predictive control, which is the high computational load and high steady state ripple due to the using only 1 voltage vector during 1 control period and expensive compute platform. And following to this drawback of the traditional methods, a discrete space vector modulation is employed to avoid these disadvantages. The concept of the DSVM was implemented to reduce the ripple in the waveform of the torque and the current. The major concept of the using DSVM in FCS MPC is for using additional vertical voltage vector beside the real voltage vector in order to scan the entire control region of the converter. In the figure A here, where the converter has 3 discrete real states, which is a round mark, and 3 additional virtual the square mark in each sector. Then 2 voltage vector will be applied for each sample instead of 1 voltage vector. It means the switching period will be divided in 2 parts. For example, 0 voltage vector will be applied on the first part, and the second part 1 voltage is applied. And to achieve the better result, 3 voltage will be applied per period as shown in the figure B. So to validate our methods, or after presenting the theory of the traditional FCS LPC, we will analyze the behavior of the electric drive system using the permanent magnet synchronous motor by this technique. It means the traditional technique. Here, figure A and figure B show the motor speed and the tracking error. According to this figure, the measured rotational speed varies depending on the reference, and we see that there is a good tracking dynamics, but there is a large overshoot at the startup and when changing the speed. In addition, we note that the tracking error is almost zero during all the simulation time except in the start and the speed change. Note that in figure of the speed is not strictly superimposed on its reference. It is slightly lower than it is lower than its reference. It's no zero steady state error. So, and here these figures show the result of the direct and the quadratic current. It can be observed that this strategy keeps the direct current at zero and forces the quadratic component to react to the torque disturbance, which improves the good monitoring performance of the controller. So, and for the simulation of the proposed one, here it is the performance of the speed and the tracking of the proposed one using 2 voltage vector here and 3 voltage vector. You can see that here it's better compared to the traditional FCS MPC. It's clear that the method proposed with its 2 cases, 2 voltage and 3 voltage, and require a settling time of 0.011 seconds, while the traditional method requires a higher settling time, more than 0.05 seconds. The speed tracks its reference quickly and without overshooting. Also, the speed is strictly central symmetrical with its reference, resulting zero static error. And here, the direct current and the quadratic current of the proposed one using 2 voltage vector and 3 voltage vector. And you can see here that the 2 currents are regulated independently of each other, and it's exhibited different behavior depending on the control strategy used, whether in transient or permanent condition. And more particularly, the variable EQ or quadratic current. Concerning the conventional method, the current EQ shows a very clear ripple, whereas in the case of the multiple vector using 2 voltage vector and 3 voltage vector, the phenomenon is reduced considerably. In the proposed method, using the 3 voltage vector, it gives a minimum value of the ripple in the current along the Q axis compared to the one using the 2 voltage method and the conventional one. In addition, the ripple in the current along the D axis is small in the 3 voltage, but in the case of the 2 voltage, the ripple is slightly bigger. Here you can see in the 2 voltage vector. And for that, thanks to the contribution of the vertical vector, which reduced the undesirable phenomenon, which is ripple, and it is the drawback of the traditional one. So as a conclusion, there is always a large current ripple and the poor steady state performance due to the application of only one vector in conventional FCS LPC during one control time period. The proposed control technique is based on the discrete space vector modulation by combining the virtual voltage vector with the real ones in order to reduce the ripple in current waveform and therefore improve the steady state performance. So furthermore, also The proposed method reduces the calculation burden by computing directly the reference voltage vector from the reference current, and the results show that the proposed method, which is robust model predictive control with 2 voltage vector and 3 voltage vector, have a better dynamic response than the traditional one. And thank you for your attention.